this talk is based on two papers. One of them joined with Itai and Russ Lyons, and the other with Itai and Schramm. Okay, so first I should say that there was a slight typo in the title of the talk, and it's actually the real title is this. So you can understand that how that typo happened. Okay, so what does this mean? So we have Hansel and Gretel, and they are going to the forest with their father, who wants to kill them or actually abandon them because of their evil stepmother or something like that. And we want to abandon them in some unknown spot in the forest. But luckily, Hansel or Gretel, one of them, spread breadcrumbs along the way so they can trace their way back. Okay, so unfortunately for them, it takes the father infinitely long until they get to the place that you want to abandon them at. And the question is, if they only look at the breadcrumb, and they have, of course, no idea, the breadcrumbs are not numbered or anything, so they can't just retrace their step. They can just walk randomly to other breadcrumbs that they see around them. And the question is whether they return home with probability 1. Almost sure. Okay. Yes, no, it's okay, it's a complicated forest. Okay, so enough with the completely hypothetical abstract nonsense. They're bears. I didn't mention that. Anyway. Okay, so let's move to more concrete, realistic object. Okay, so I will have many really trivial things for many people, but maybe some people don't have all the background, so I want this talk to be as complete as possible. Okay, so we have a graph, an infinite graph, locally finite, all the degrees are finite, not necessarily bounded. Then we have a simple random walk, which means that we just pick a neighbor randomly, uniformly, and go to that neighbor. And the simple random walk is recurrent if it returns with probability 1, like Hansel and Gretel want to do. And otherwise we call it transient. Okay, and we categorize the graph accordingly, according to whether the simple random walk is recurrent or transient. And now we look at the path. So even though I said breadcrumb, actually these breadcrumbs are very, long and thin. So they actually correspond to edges in the graph. So we mark all the edges that the simple random walk has crossed, and we call this the path. And so here is the answer for the question about Hansel and Gretel. This graph, which is the random graph, is always recurrent. I mean, almost always, a recurrent subgraph of the original graph. So, of course, if the original graph was itself recurrent, then this would be trivial because we just return infinitely many times to the origin, and then it means that we visit every edge, we cross every edge, and this means that we just cover the entire graph. So this is not the interesting case. So from now on, we assume that the G is transient and forget about the possibility that it's recurrent. And yes, and this theorem, there are probably easier way to see this, but this also implies that the converse to what I just said is also true. If we cover everything, then this means that the original graph is recurrent. We can't have a tangent graph in which the path covers the entire graph. Okay, so this is a nice thing to know.
Can you explain again the theorem?
Yes, so we have a graph, which is, let's say it's transient. We start a simple random walk. Every edge the simple random walk crosses, we paint red. And then we look at the red subgraph. This is some random subgraph, depending on the random mark, where it started, everything. And what I claim is that with probability 1, this subgraph is a recurrent graph itself. Meaning that if I start a simple random walk on it and only on it, it will return with probability 1 to the origin. Okay. Okay, so we're going to use the electric network interpretation. So I realize that many are very familiar with it and some perhaps are not. So I'm going to explain everything that we need. So it might be boring for some people, but that might be better than both boring and unintelligible for other people.
But it's a little bit surprising that this theorem was not found before you were born or something like that, right?
Well, I'm much older than I look. I mean,
before I was born.
yes, but you're right in that Itai also like to say that this is a recently discovered classical theorem. Okay, okay, so what is the electric network interpretation? So I'm just going to do some hand waving now and explain it with more detail later. So we take the graph that we have. Let's say, suppose that it was just finite graph, and we just assume that every edge is a unit resistor, and we look at it as electric network, and we can measure what is the electric resistance between some 2 points. And similarly, we can do this for infinite graph, measuring the resistance from some point to infinity, which will make this notion precise later. And the point is that the graph is recurrent if and only if this resistance is infinite. Okay, and actually it will be more useful to work with effective conductance, even though if somebody is not familiar with that, that might be less intuitive. But this is just 1 over the resistance. Okay, so the graph is recurrent if and only if the effective conductance is 0. Okay. So now let's generalize this a little bit. So instead of a simple random walk in a graph, we have a weighted graph, and we do a simple weighted random walk, meaning that we just use each edge with proportional to its weight. So this is like having multiple edges. If we had x and y, we had 2 edges, we had double the probability of moving from x to y. It's not exactly the same, because if we had 2 edges and we crossed from x to y, we just painted one of them. Okay, and then we had the next time we have some probability of painting the other. And in this case, we have just we have just one edge. We just color it red once. So it's not completely the same. And therefore, it's not completely trivial to say that theorem 1 is also true when the simple random walk is weighted. It's on a weighted graph. But of course, the path itself has to be unweighted. To see that this is the case, let's consider a graph on the integer and having conductances of 1, 2, 4, etc. So this is a transient graph. You run away to infinity, and if you use these weights in the path is just everything. Okay, if you use the weight in the path, then of course you would get a transient graph. And also, we actually use the fact that G is transient here in the sense that if we have a recurrent graph, recurrent weighted graph, but path is unweighted, then we might get a transient graph. Okay, so to see that, you just take something like, let's say, Z3, but you put weights on it that would make it a recurrent graph. Okay, just put low conductances or high resistances. So if it's recurrent, then we're just going over all. The path is just everything when the path is unweighted, so the path is Z3 and it's transient. Okay. Well, but again, from now on, G is transient, and let's forget about this remark. Okay, so let's instead of just painting red, let's count the number of times we cross each edge. So here's something slightly stronger than theorem 1. If we look at the new graph in which we put conductances or weights according to the number of times that we crossed an edge, this is also almost surely a recurrent network. Why is this stronger? So this is like putting multiple edges. Every time we cross an edge, we put an edge in the path. Okay? And this implies theorem 1 because we have monotonicity. If we have a bigger graph, and the bigger graph is recurrent, then this means that also the smaller graph is recurrent. We'll also talk, expand on this point later. Okay, but we can actually say something slightly stronger yet. So instead of looking at some random subgraph, look at the expected number of times that you cross some specific edge, and look at the new graph and the new network, which is the original graph with weights that are according to this expectation. So we claim that this is a recurrent network. And this is not almost surely, there's no probability here, this is just a new network, just the same graph with new weights, and this is always a recurrent graph. Okay, and why is this stronger? Then this is because the effective conductance, if we measure what is the conductance, when I say effective conductance, this is just the conductance of from some point to, let's say, infinity. Then this function is a function of the weights of the conductances on the edges. This is a concave function. I hope that this is concave. Right? The dictator, have any questions? No? Okay. Okay, so what does it mean that it's concave? So this means that if the effective conductance of this network, this is the expectation that there's some some random variable, some distribution of n. If this thing is 0, this is exactly what this theorem is saying. Then this means that the expected effective conductance of the network is also 0. Okay, because again the function is concave. It looks like this. Okay, so the point on the line between these 2 points here is below the point here. Okay? But this second thing is exactly the same as saying that the effective conductance is just almost surely 0, which is exactly theorem 2. Okay. And a nice and somewhat unexpected corollary is that even if you take, 10 or 10 million simple random walk and you look at the paths of all of them together, this is also recurrent. And even if they had some dependence between them, some kind of thing, as long as each of them is still a simple random walk in itself. Okay, because everything stays the same. This is all, relying on expectation and not on any other consideration. Okay, well, this was very. It was so unexpected, at least for me, that in the first version I wrote that this is also true for finitely many independent simple random walks, not noticing that you don't need the fact that they're independent. Okay, so this is the first part of the result. Okay, so if we have, suppose that we have some graph, infinite graph. So a cutedge is an edge that if you remove it, you separate some point from infinity, meaning that this point is now, this vertex is now in a finite component. Okay, so if we have Euclidean lattices, and of course other graph, but typically Euclidean lattice, it is known that was already known that path has infinitely cutedges, almost surely. So this already implies that path has infinite resistance because each of these cutedges contribute a resistance of 1 to infinity. So it was already known before, just a second, that path is recurrent. Yeah. I'm sorry?
Did you
What, is it always true? Or?
No, it's D. D, the dimension is a dimension greater than 4.
Ah, yeah, yes, it's true in any dimension which makes it transient. Yeah. Yeah. Okay. So in a sense it was already known, but of course nobody said it like that, but it was known. Okay, so the natural question is whether this happens all the time. Maybe the reason that we have the path is recurrent is because we always have infinitely many Cutedges, and so this is not true in general. So James Nansen first provided an unbounded degree. It was not exactly phrased like this, but basically it yielded an unbounded degree example for this. So what time is it? Okay, so I think that I will skip talking about the conjecture in which this came up, although it's very interesting, and if you want you can ask me later. Okay, and their example, they also noted that even though there are only finitely many Cutedges, the expected number of Cutedges was infinite. And they asked whether this is always true. Maybe, if the first thing is not true, maybe the second is. Okay, so we have some answers. There is actually an example of a bounded degree transient graph that just path of only finitely many Cutedges, and furthermore, there are actually very natural examples for this. So if we take a horn in ZD is just something which looks. What is the eraser? It's not. It's not that important, but it's just something that looks kind of like this. And we take the. Oh, yeah, okay. So if we choose the function here, and this is also this is three-dimensional, of course. And if we choose the function here appropriately, just to make it just barely transient, then we get only finitely many Cutedges. That's okay. Just just this thing for now. Yes, it's called a horn here and in the paper, but it's actually more like a cucumber. But the expected number of Cutedges is always infinite, as it turns out, and the argument is very nice and simple, and we'll show it. So these are the results. Any question about them, or we can move on to the proof and background? Okay. Okay. So what is electric? Yeah.
It's not the number of Cutedges. Then is there any other thing that you can say it's because of this or it's because of that it's required?
What in the on the cucumber or something like that, or in case that you don't have infinitely many Cutedges? Well, it's because of our theorem. I really have no. I mean, you will see the proof, and I really have no, anything more specific in the case that you have only finitely many. I mean, for example, I'm not sure. I didn't think about it, but you could ask whether you have, instead of Cutedges, instead of infinitely many Cutedges, maybe you have a sequence of cut sets such that the sum of 1 over the sizes is infinite. Yeah, so I'm not sure that happens, but maybe. Okay, so what are electric network and what is the connection and everything? So we have a weighted graph, and we define two functions. One we call one the voltage and the other the current, and they have to satisfy Ohm's law, meaning that the current is proportional to the voltage difference along the edge, and the proportion constant is exactly the conductance of this edge. And Kirchhoff's law, which says that the current is preserved on every vertex except for, A and B. We think of a current flowing from A to B, something like that. So if we put these two laws together, what we get is that V, the voltage, is a harmonic function. Okay, so you just take this thing and you replace this by this, and then you get this equation. So a harmonic function just means that the value of the function at some vertex is the average, here the weighted average, among its neighbors. Okay, except at A and B, where Kirchhoff's law don't hold. Okay, and in particular we have the fact that the voltage and hence also the current are actually determined by the values of VA and VB. So this is true for any harmonic function is determined by the boundary condition. And the boundary here is just A and B. Okay, so now let's take a simple random walk and let's look at the probability that the simple random walk, when you start at some vertex, hit A before it hits B. Okay, these are all finite network for now, so this probability is, well defined in the sense that the sum of hitting A before B and B before A is 1, everything. So this is also a harmonic function because this probability is exactly, the probability when I start here is exactly the average among the places that I'm going to be at the next time step. So this is exactly the same equation, and since it's determined by VA and VB, here we have P of A equal 1 and P of B equals 0. So this is exactly the voltage of. Okay, so this is the basic connection between an electric network and random walks. Okay, so now what is the effective conductance? Is that's that if we want to replace some network with a single edge. Okay, so we just take the proportion between the voltage difference and the current that we get when we put this voltage difference in A and B, and this thing is the effective conductance. So that's exactly the definition. Okay, so what we have here, this is just the total current flowing out of A, and it's also equal to the total current flowing into B, and divided by the voltage difference. Okay, so how is this thing useful to us at least? Look at the probability of escape from A to B. So we start a simple random walk at A, and we ask what is the probability that we'll hit B before returning to A, but of course we don't count the time 0 here. So this thing is exactly the average among all the vertices that the simple random walk will go to in the next step, okay, and of the probability of hitting B before A. So V was the probability of hitting A before B, so this is 1 minus V, okay, but CAY times 1 minus VY, this is just the voltage difference, and this thing is just the current, and since V of A is 1 and V of B is 0, what we have is here is just the effective conductance. And it is divided by C of A, the sum of the weight of A, the sum of weight. Yeah. The what? Oh, excluding time 0? Yeah, no, we just don't count time 0. Time 0, we start at A, so we don't say that we already reached A. Okay? We start at A, and we ask whether when we start a simple random walk, we return to A first or to B first, but of course we don't count the first time. Okay. So this means that if we have a finite network, when we think of C of A as something fixed, then the probability of escape is exactly proportional to the effective conductance. Okay, So how do we define this for infinite network? We just take the limit of the probability of escape or the effective conductance to some large ball. Okay, so this is just a definition, and the fact that we use ball here is completely irrelevant. We could have used any other sequence of graph exhausting the original graph. Okay, so this means that G is recurrent if and only if the effective conductance to infinity is 0 from some vertex, because this is exactly the probability that we will visit a faraway vertex before returning to the point that we started. And if we were visiting a very infinitely far away vertices before we're returning, that means that we never return. Okay. Okay, so that's the first thing I stated about the connection between electric network and simple random walk and recurrent. Okay. How do we show monotonicity and concavity, which we used to deduce theorem 1 from theorem 2 and theorem 2 from theorem 3? So we defined the notion of energy. So the energy is just this thing, okay, the sum of the square of the voltage differences, and the energy of the graph is just the sum over all the edges. And as it turns out, we can instead just look at the effective conductance and multiply it by the square of the voltage difference of the entire network at once. So if we calculated the effective conductance, we don't need to sum up all the energies of all the edges. That's not too hard to see. And we have a very nice thing called Thomson's principle that if we want to calculate the energy, of, let's say if we want to bound the energy, we don't want to calculate it, we don't have time for that, then we can just take any function of the vertices and calculate the energy according to this function. This is not the real energy, but let's call it the energy of this function. And this is always bigger, and actually the infimum of these, or the minimum of these, is the real energy. And this is quite easy to see, at least for finite network, probably also for infinite, in that if suppose that we have some f, and this f is not harmonic, okay, then this means if we take some point in which f is not harmonic, and we change the value of f there to be the average of its value on its neighbors, then we get something that is slightly lower. Okay, so this means that when you pick f that minimizes the energy, we get a harmonic function, which is the voltage. Okay. So what we have now is that the effective conductance is both monotone and concave. Why is it monotone? Well, of course, this expression, okay, is of course monotone for every f. So the minimum or the infimum over all f is also monotone. When I say monotone, I mean of course monotone in the weights, in the conductances cxy. Why is it concave? Well, for any fixed f, this is just a linear combination, with positive coefficient, but that's not important, of the c's. So for any fixed f, it looks something like this, and we take the infimum of everything, the minimum of everything, so we get something like that. Right? This is the function that we get. So of course, this thing is going to be concave. Each of the linear combination is concave. Okay. So this immediately gives us, that theorem 3 yields theorem 2, and theorem 2 yields theorem 1. Now, something that we're going to need later, let's write down that the things that we're going to need later, that there is a dual form of Thomson's principle which gives us the following fact, that if the effective conductance is to infinity is positive, meaning that the graph is transient, then the effective conductance from some large ball, from some large set far away from the origin to infinity is going to be large. It's going to tend to infinity. And this is it just seems reasonable, this thing. So let's write down the things that we're going to need later. So one of them is that the probability of escape is just the effective conductance over Ca. Okay, that's one. The second thing is this thing. So the effective conductance from some x to infinity is positive if and only if the effective conductance from some large ball to infinity tends to infinity. Okay, we're going to need a couple more facts. They're very simple, though. Okay, so the other thing that we're going to need is reversibility. What is reversibility? It means that the probability of the random walk to do a walk backward and forward and backward in time is essentially the same. Okay, what does this mean? It means that the probability that the random walk starts like from x0 goes to x1 to xn. This is just this thing by definition. And if we look at these pairs, then we get exactly the probability of doing the same path backward, okay? Except that of course this thing cx0 is not cancelled by anything, and we need an extra term here of cxn, which we don't have. So it equals this time the ratio between the weights of the two vertices. Okay, so in particular it gives us the following thing. If we look at the expected number of time that we visit, we started x, we look at the expected number of time that we visit y, and suppose that the graph is tangent, so this is a finite number. So this is also reversible, because this is exactly like the sum over all paths starting at x and ending at y of the probability of this path. Okay? So this is exactly like the sum over all paths from y to x of the probability to do it backward, time, of course, the ratio between the weight. Okay, so this is another fact that we will use. So let's write it down. So let's write it like that: cxy over. So that's g is gyx over cx. Okay, that was simple enough. And this is even simpler if we have the probability of hitting y at all. So the expected number of visits to y when we start at x is the probability to hit y times the expected number of times when we start at y. Okay, so this is really trivial, but we're still going to write it down. So we have this xy, g, y, y. And last but not, well, maybe it is least. So, of course, if we look at the expected number of visits to x when we start at x, it is just 1 over the probability of escape, because the distribution is just geometric. Okay? Every time we return, we have the same probability of running away to infinity and never seeing this vertex again. Okay, so we can already combine many of the things that I wrote. Probability of escape from x to infinity. Okay. Okay, so if everything is clear, we can give the proof of theorem 3 and then of the other theorem. Okay, so we fix some vertex and we define the voltage function according to this vertex. This is just the probability that we will ever hit the vertex, including time 0. So v of x0 itself is 1. Okay, so we want to calculate this thing, right? We want to talk about this network. I wrote here path is recurrent, but I actually meant that theorem 3, which means that the network with weights that are the expected number of times that we're going to cross this edge is recurrent. Okay, so it's E of n. So what is E of n of some edge? Okay, so this is just the expected number of time when we start at the origin, we start at x0, that we will hit x, and every time we are at x, we have this probability to cross edge xy. And of course, we're also talking about the other direction. Okay, so we have to add this as well. Okay, so we're going to use reversibility. So this thing here, I hope you can see that, and we're just going to use it on these two terms. So instead of gx0x, we have gxx0, and we just divide by c of x0 instead of dividing by c of x. Okay, that wasn't too bad, I hope. So it's nice because we now have this common term in both things. Okay, so what is gxx0? So this is the expected number of times that we're going to visit x0. So as we said here, this is just the probability that we will hit x0 times the expected number of times that we will hit x0 when we already start there. So this is just v of x times gx0 x0 and v of y times gx0 x0. Okay, and the last thing is that if we put g of x0 x0, it's just 1 over the escape probability, and the escape probability is just the effective conductance over Ca, and what we get is that this term is exactly 1 over the effective conductance. Okay, so we have a nice expression for the expected number of times that we are going to cross an edge in either direction. And what's nice about it is that it's exactly so this is the new weight of this edge. It's exactly the old weight times some factor. So this is not very important, although it will cancel out nicely, but because this is just some constant. And what's important is that we have this factor, just v of x plus v of y. Okay, it's just the probability to return from x or from y to x0. Okay, so how do we use this? What do we do now? So suppose that we take our graph and we draw it along the along the voltage. So here the voltage is 1. Here this is x0. V of x0 is 1, and we have some other vertices here and here and here, and they have some lower voltages, and this is a voltage of 0. We never actually reach a voltage of 0, but as we go on to infinity, we come close to a voltage of 0. So in a sense, this is infinity, and the graph looks, well, kind of like a cucumber. So let's take a look at Vt. What is Vt? Well, if this is t, then this thing is Vt. And I want to look at the effective conductance between Vt and infinity. Okay, so in fact, what I want to show is that if the not path but V with the new conductance would be recurrent, if it would be transient, then this thing should be very high. Okay? But what I want to show is that this is bounded, and therefore the new network we defined is actually recurrent. Okay, so if we have some edge that is outside Vt, so it's here, okay, x and y, so this means that v of x and v of y are small, they are less than t. So in particular, if we take this expression, we can bound it by the old conductance divided by something, which I said is not very important, times 2t. So this means that if we look at the effective conductance in the new network with these weights between Vt and infinity, what we have is the effective conductance in the old network, okay, because these are the old conductances, time at most this factor, okay, because every edge is multiplied by at most this factor. Okay, so we only have to bound this thing. But, and this is crucial, this thing is actually bounded by 1 over t. Okay, so why is that? So what am I saying here? So suppose that, for a moment, just the effective conductance between here and infinity is exactly 1. Okay, so this would mean that if we look at the current, we have a current of exactly 1, okay, flowing from x0 to infinity. And now we look at exactly the same current, but we only look at it from this point to infinity, the voltage is between t and 0. So we have the same current, that's a unit current, but it's not very important, but the voltage difference is just t instead of 1. Previously we have a voltage difference of 1. Now we just have a voltage difference of t. So this means that these two things are actually equal. Okay, so I cheated a little bit. Okay, and where did I cheat? So it's there are two cheats here. And okay, I will address this in a second. So when we put these two things together, we just get 2. So no matter what t we take, no matter how big a portion of the graph we take, the effective conductance to infinity in the new network is just going to be bounded by 2. So this means that it can't be the fact that this was positive, the effective conductance was positive, because we just wrote it down. And what I write down 3 times is 2. I didn't actually write it down 3 times, but so that's it. That's the whole proof. Where did I cheat? So the main thing perhaps is that there are some edges that cross this boundary. So sometimes v of x is greater than t and v of y is less than t, and these edges are, they do count when we look at the effective conductance between this set to infinity. So we can overcome this, and we do this by subdividing edges. We just add a new point here, and we show that we didn't do anything bad by subdividing. So we just got a bigger network because of this subdivision, and then what we get is that all the vertices here are exactly on the border. They are nothing like that. No edges crossing this border. And the other thing, the other place where I cheated, okay, 5 minutes, that's good, is that I drew this picture as if all infinity is over here, but that's actually not true, because if I just add here like a path or any recurrent graph, then all of these have a voltage of 1, and the voltage doesn't go to 0. So what does it even mean that I take this and calculate the effective conductance to infinity? After all, these also include some vertices at infinity. So this is okay. So I'm not going to talk about it, but this is a technicality, because this thing is always recurrent. Okay, so we can define the effective conductance between here and infinity, and everything does work out. But even if it bothers you, if you look at nice graph like, I don't know, Z3 or something like that, then this thing is always finite. Okay, so it doesn't happen a lot. Okay, any question about this before we move on? Okay, so I assume that the fact that there are no questions is not because I'm suddenly a really spectacular lecturer, but because I lost everybody. So the next the next part is going to be about theorem 5, which has nothing to do with this, and you can wake up and look at the proof of this theorem. So theorem 5 is the fact that we have, thank you, the expected number of Cutedges is always infinite. And this is actually true for any Markov chain, not just reversible one. But let's for the moment assume that this is a simple random walk. This is a reversible Markov chain. And again, we have V of x. This is the probability of to hit x0. So V of xn is actually a martingale as long as we don't hit x0. So okay, this is trivial because V is harmonic function, straight from the definition. So this V is we start at 1, and we know that we tend to 0 because if V of xn would be, I don't know, more than half at infinitely many points along the path, then this would mean that I would have a probability of at least half to hit x0 in the future, but I only hit it finitely many times. So this means that V of xn has to tend to 0. But of course it's always positive, and here I use the fact that it's reversible. I always have some chance to return to x0, no matter how small. So this means that we have actually a sequence of not exactly local, but minimum so far. Okay, so we start at 1. Let's say the first step we already moved to, I don't know, half. So this is the first minimum. Okay, and then we go to 3/4 and etc. And then we suddenly again hit, I don't know, 1/4. So it's less than 1/2. So we have this sequence of times and the voltages at this time. Oh, sorry, voltages at this time. Okay, and it's just a decreasing sequence tending to 0. So suppose that we just hit one of these. Write it down. If we, this is V, so this is the minimum, and then we suddenly hit a new minimum. So what is the? So this means that everything until that time is above this line, and suddenly we go down to this point. So what is the probability that we will ever hit any of this point? Of course, it's bounded by the probability that we will ever be above this line. Okay, and well, it's a martingale, so this probability is at most Vi over Vi minus 1. Okay, but if we never hit any of these points, this means that this was a cutedge. Okay? So the probability that this is a cutedge, if we already know these two numbers, okay, is at least 1 minus Vi over Vi minus 1. Okay. So what is the sum of these numbers? So I claim that it's infinite because the product of 1 minus these numbers is 0 because this just cancels out. So again, I treated at least slightly because these numbers are not known, beforehand. You write them down as you see the path, but it still works out. It's not a real problem. Okay, so again, why does this work for every Markov chain? So we only use the fact that it's reversible here, that we say that V is always positive. What happens if it's not always positive? That means that sometimes this point is 0. If it's 0, then we actually stay at 0 from now on, and we gain no more information from observing V along the path. But it also means that this edge again was a cutedge, and this time with probability 1, okay, because we can never go back, and then we can just apply the same logic again, only starting with this point. Okay, so we have a new V, called V2, and we use this V2, and again it's a martingale and everything, and we do this again, and if we ever hit 0, we define V3, etc., etc. So either we hit we hit 0 infinitely many times, in which case we have infinitely many Cutedges, or we don't, but then we get still an infinite expectation because at the v that we stop, we have the same calculation. Okay, that's it. 11:30.